There's a lot of traffic.
A lot of traffic?
There was like together.
Oh, you took the I-70?
Yeah, there was like, and then my GPS, found me.
I see. Did it work?
Yeah, it was pretty much faster than stuck in. You go near I-70 and you see that.
There's a parallel.
On I-70, like everybody's staying there.
Really?
But it's like this road is much harder than
All right, good.
Oop. Is it time in our atomic clock? Okay. Everybody ready? Yes? Good. Okay, so I hope you had a really nice weekend. We had some nice hikes. Some of you went with me on Saturday and Sunday. And at least I know some of you went to the sand dunes, right? And before you went to the sand dune, you asked me if I can help you with returning the equipment. And I said, sure, as long as you answer one question through the hike. And then Saturday night I got an email, we don't need your help. And so I was wondering if you still solve the question. So the question that I asked, and I really hope you discussed it in the hike, was what is the mass of the B meson? That's the first part of the question. And how it is relating to hiking in Colorado. Okay?
So we did discuss this.
You did?
Yeah.
Good. And the answer is?
It's let's make sure I get this. 5,280 MeV, which is like a mile.
I'm so happy. That was definitely.
Thought of you while we were camping.
I'm really happy, That's the best one can hope as a professor, What else you can hope? That all your students go camping nicely and all they think about is what is the mass of the B meson. What else? So for those of you who didn't got the thing, let me tell you my little story. So when I was, I sound so old, like half of my lectures are stories. Anyway, but when I was your age, and I was in Tassie in 1994, you heard it before, and we went hiking, and Tom took us hiking up there, and then it was this sign of elevation, 1 mile, 5 to 80 feet, okay? And as someone who do B physics, back then it was all my life was 3 years, and now all my life is whatever, 20-something, immediately jump at you that the mass of the B meson is 5 to 80. And one thing that you have to remember, and that's completely true. It's much simpler to remember two things than one thing, okay? So I don't know how many of you here are not American, did not born in the US? Wow, I think more than half. Okay. So for those of you like me who never born in the US, and you never know what a feet is, and of course, the last thing you know is how many feet there is in 1 mile, okay? Because in all other normal systems, it's some factors of 10 or 12. And then there's this amazing, completely natural scales of feet. Feet is much more natural than a meter, right? Because feet supposed to be like this, while a meter is completely arbitrary unit. So it's much more natural. And a mile is also much more natural than a kilometer. Why? I don't know, but supposedly, right? So how many feet there is in 1 mile? How many of you, I assume all Americans know it, right? Because, yes? No? More or less, in 500 feet turn left. So it's about like a quarter, tenth of a mile, right? So those of you who don't know how many feet there is in 1 mile, and it might be very useful one day. You never know when you will need it, right? And for those of you who doesn't know or who do not know what is the mass of the B meson, then comes this amazing coincidence, okay? It's one of the most unexplained fine-tuning of nature. That the mass of the B meson is within 10 to the minus 4 of the number of feet in a mile, 5 to 80, okay? Good. Check your PDG. Open your PDG, and then it's very, very nice to look for other such coincidence, okay? And then I was sitting on lunch with someone else, and he said, oh, the mass of the tau. Who was this guy? Who was the mass of the tau? Yes, thank you. The mass of the tau is also the same as declaration. And then we had a long discussion because what is the mass of the tau? What is the the year of declaration, the independence? 1776. And what is the mass of the tau? 1777. So we are not so sure how precise. However, if you look for one extra decimal place, then the mass of the tau is 1776.8, right? While the declaration was in July 77. Okay, so actually we are getting close. So anyway, so keep looking, and if you have more of those, let me know. Okay, I love them, so I can remember. And if not, just memorize the PDG. It's okay. So what we did last time. Let me come back to physics. So what we did last time, I made the big deal about the fact that the standard model, that in nature, flavor is not generic. Okay. So last time, we said the following things: flavor in nature, flavor is far from is not generic. Is far from generic. Right? Generic. And what we mean by this, we say, and how the standard model explain it. So instead of saying what is happening in nature, let me give you already the standard model explanation. The standard model explain nature. So the standard model, there's only the charge W's, the W plus minus, is the only one, the only source of flavor breaking. It's only come from the W plus minus, and that we emphasize this has to do with any standard model, and then with our standard model, in additional to the fact that it's only come by the W plus minus, there's also the fact that there's many small parameters. There's many small parameters, many small numbers. So this fact, the fact that it's only the W that make flavor change unitrack, and the fact that we have many small numbers, this combination make the flavor sector very far from generic. Okay, and I didn't emphasize it last time, but we kind of touch it. That's really in contradiction to the gauge sector. If you look at the gauge sector is kind of generic. Okay, just say, well, okay, I have this kind of thing. The loop correction are of order 1/16 pi squared, as they should. Everything is what you kind of expect from whatever. In flavor, it's a different story. Okay, so what I want to do today, I want to keep getting a little bit deeper into the question of why the standard model is not the generic, and how the standard model takes care of these kind of things. And then I want to start, hopefully, to get into how we do beyond the standard model. Oops, but that's probably the wrong one. Yes. Okay, so I will. Okay, that's okay. We don't really need it. That was last time. Okay. So one thing I want to do before I want to do first is I want to discuss a little bit about the global symmetry of the standard model and how it is related to flavor. So we know that global symmetries are accidental symmetries, are not something that we impose. They're something that are an output of model building, right? The way we do model building, we impose only local symmetries, and then if we have an output, the output is a global symmetry, and it's there only because we keep renormalize. If we add non-renormalizable terms, these accidental symmetry are not there. And in the quark sector of the standard model, what is the accidental symmetry? What is the global symmetry of the standard model, of the quark sector of the standard model? The full standard model. That's when you don't put any Yukawas. At the very end of the day, in the full standard model, what survive? Just baryon number, right? So we have the full quark sector of the standard model have only U1 baryon as an accidental symmetry, as a global accidental symmetry. And now what we like to ask is what's really how we got into this. And if we treat the Yukawa coupling as a small parameters, you can say, oh, we start with some very large symmetry, something like U3 cubed for each of the fields. But if I only consider the strong and the electromagnetic interaction, each flavor has its own U1 symmetry, right? So if I turn off the weak interaction, and we think about the weak interaction somehow as a small parameter, if I only have QED and QCD, so under QED and QCD, the global symmetry is U1 to the 6. That is, each quark flavor has its own U1. That is, under U1, say U1 charm, only the charm is charged and all the rest are not charged. So we know that QED and QCD cannot let any of those things, any flavor violation. It's only the weak interaction that have it. And now we ask how the Yukawa coupling break this U1 to the 6. Okay? And if I put only one Yukawa into the game, let's say I put only Y down. Let's say there was no Y up. How Y down would break this U1 to the 6? If I have only Y down, what happened to the U1 to the 6? U1 to the 3. U1. Because what's happened when I have Y down is just like what we have in the lepton sector, right? That is, we only have masses for the down component, which is just what we have in the lepton sector, which is we only have masses for the charged lepton. And then Y down break U1 6 to U1 cube. That is, each pair of U1s become one U1, right? So U1S and U1 U and U1D become U1 of the first generation. U1S and U1C become U1 of the second generation, and U1T and U1B become U1 of the third generation, just like we have in the lepton. Okay? And clearly, if we have only U1 up, only the Yukawa of the up, it will be the same. However, if we have both, then it breaks down. Okay, so if we have this, but if we have Y up and Y down, it breaks down to U1 baryon number. So this is, again, a very general feature of all standard model. It's not our standard model. In our standard model, what's happened that these symmetries become somewhat approximate. Why they become somewhat approximate? Because we can think about Y down and part of Y up as small numbers, right? The top is large, so we cannot think about the top as a small number, but the bottom is still kind of small, because what is the Yukawa of the bottom is over the 10 to the minus 2. So we can definitely think about all Y down as small. So then we can think about the U1 cubed in some cases as an approximate symmetry. Okay? So that's become important later. I just wanted to mention it here before we go on. Okay, so now I want to discuss flavor change in neutral current and why they are so important and how the standard model take care. Now I can do this, and then I can move it up afterwards. Okay.
So how much of this is true because the powers are different?
So yes. So clearly, if we had degeneracy, the situation would be much more complicated, right? So let's say that that we had a degeneracy between one sector, then we'll have a U2 symmetry rather than a U1 cube, right? So if the three masses were the same, we'll have a U3. If we have two degeneracy, we have U2 cross U1. And since all three are non-degenerate, we have U1 cubed. And it's really good to understand those, because to some degree we say they're almost degenerate, because the mass of the D and the S both are very, very small compared to the weak scale or compared to lambda QCD, and therefore we get this kind of symmetry. Okay, but I really just wanted to touch upon it, and I want to move to flavor change in neutral current. So in the standard model, we say there's no flavor change in neutral current at tree level, and that's a very big deal. Because there's no flavor change in neutral current at tree level, flavor change in neutral current is suppressed, and most of flavor changing happens through charge interactions through the W. So I want to discuss how the neutral current that we have, what kind of mechanism the neutral current kind of developed in order to make it flavor diagonal. Okay? And it's really important to understand those, because basically we use those tricks that we use for the standard model when we go and we do model building for BSM. So let me start with the following questions. What bosons, of course we only need boson, because only boson can generate currents and forces. What neutral bosons we have in the standard model? And all of them, all the coupling of all of those bosons are diagonal in flavor space. So let me ask you the first question. What are the neutral bosons of the standard model? Photon, Z, Higgs, gluons. Very good. So there's kind of four of them Okay, the gluon have 8 degrees of freedom, but there's 4 kinds of them. Okay, and we know that all the coupling of all 4 gauge bosons in flavor space are diagonal. Okay, they are not, may not be universal, but they are diagonal. Universal, it means that they are the same, right? Is the photon coupled the same to all flavor? Not really. It's coupled to up and down differently. Is the Higgs coupled the same for whole flavor? No. Is the Z coupled the same? Also no. The gluon actually, yes, for all the quarks. But the question is why all of those are coupled in a diagonal way, and that's what I like to explain. Like what really is the important ingredients of the standard model that made it. Okay? So let me start actually with the photon on the gluon, because the photon and the gluon actually has the same mechanism that guarantees that the photon and the gluon have no flavor change in neutral current. So what is the mechanism that guarantees that the photon and the gluon must couple diagonally to quarks? Sorry? Speak up, I don't hear it. Not really. What makes sure that the photon and the gluon couple diagonally? Gauge invariant. Okay? It is gauge invariant. As long as the symmetry is unbroken, it's guaranteed that it's coupled diagonally. And if you like to ask how do you know it, the answer is when you have the photon and the gluon, any gauge symmetry that is unbroken, the coupling comes only through the kinetic term, right? So when we work in with canonical kinetic term, that is if we diagonalize the kinetic term, automatically we diagonal the gauge interaction. Okay? So that's actually a very strong result. As long as your gauge symmetry is exact, your gauge coupling guaranteed to couple diagonally. So if someone asks you, take any model and you do whatever calculation in the model, and you end up that you have an exact gauge symmetry that's coupled non-diagonally, you know that that's a mistake. Okay? And I had students come to me and said, oh, look, I did the calculation. And what I say, I know you made a mistake. I don't want to go over all your calculation. I just know that you made a mistake if it's the gauge symmetry that guaranteed. Okay? So this is quite good, but actually it's not very useful for beyond the standard model physics, because when you do beyond the standard model, all the gauge symmetry that we add eventually are broken, right? We don't add any exact gauge symmetry. But that's actually kind of nice to understand for the standard model. So now let's move to the second one. And the second one, I want to explain why the Higgs coupling is diagonal in flavor space. Okay? And let's see. Why the Higgs coupling is diagonal in flavor? What really makes it diagonal in flavor space? The Yukawa coupling is completely arbitrary, right? So you have some arbitrary Yukawa coupling. And what's really happened such that at the end of the day, the Higgs couple diagonally, right? The Higgs couple only to BB bar. There's no coupling of the Higgs to B and S, right? It's aligned with the mass matrix. That's really the point. And the mechanism, which is called alignment. Okay, because we have this alignment. Alignment. And that's a very, very nice trick, and we use it later on when we do model building. The idea is as following. You have completely arbitrary matrix. However, for some reason, the same matrix that diagonalize this arbitrary matrix is also the same matrix that diagonalize the mass matrix. Okay? So when we move to the mass basis, we also diagonalize these things. For the Higgs, it's rather trivial, right? All you need to know is that you say, oh, let's write the Yukawa interaction. So the Yukawa interaction is something like this, right? Something like, say, Ui left, Uj, right? And the mass basis is defined when this Y up is diagonal. And clearly when Y up is diagonal, also the coupling of the Higgs is diagonal. So this alignment is kind of very trivial, right? Obviously, when we diagonalize, because it's the same matrix, so when we diagonalize it, we're also diagonalizing the mass of the Higgs. Okay? So we see here, actually, that the standard model, many times we hear, why in the standard model there's only one Higgs doublet? And the answer is, well, it's the minimal choice, and when we do model building, we usually want to do minimal choices, right? Why to add two Higgses when one would do the job? However, what happens if we have two Higgses? If we have two Higgses, do we have a Higgs flavor changing interaction? Yes. Generically, yes. Right? I really hope that you see it. Because what's happened when we have two Higgses? When we have two Higgses, what's happened is that we have something like this. Y up 1, H1 plus Y up 2, H2 times whatever U bar U. And what give mass? What give mass to the quarks? What give mass is the diagonalization of both Y1, A1, 2 with the corrected with V1 and V2. However, what gives you the coupling of the physical Higgs is this H1 couple only like Y1 and H2 couple. And H1 and H2 may not be the mass eigenstate of the Higgs, so there's some other rotation, etc. But in general, those rotations are not the same rotation and what diagonalize everything. Okay? So in the standard model, the reason that the Higgs couple diagonally is really only because there's only one Higgs in the standard model. More than one Higgses, we already have a problem. That's already you start feeling like how complicated it is when we go beyond the standard model, why Higgs produce so much as a problem, because it's a very delicate system. When you have one, it's okay, but when you have already two Higgses, you start having problem. Okay? And I guess all of you know that in supersymmetry there's two Higgses, right? So how Susie deal with it? So we just explained that two Higgses we have a big problem. Because I don't know if it's a big problem. We have a problem because the Higgs in general couple non-diagonally to flavor. Yes? That's right. So in supersymmetry, we say, we do have two Higgses. However, each Higgs still satisfies this. For the down type, there's only one Higgs, and for the up type, there's only one type. And in supersymmetry, we solve it by holomorphy and things like this. And so we always have tricks, some model building tricks, when we want to put two Higgs doublets to kind of make sure that we have alignment. Okay? So in SUSY, we keep the same alignment in order to have the Higgs couple diagonally. Okay? Good. So we got the Higgs. We understand how the Higgs is doing it. And now what's happening with the Z, our last one. How does Z make sure that it's coupled diagonally? Sorry? The equivalence theorem, I don't really think it's related to the equivalence theorem, actually. So the equivalence theorem just, tell you about the longitudinal part of the Z. But I'm really thinking about the transverse part. What property of the standard model make it such that the Z couple diagonally? Okay? Yes? No, so the gauge invariant is broken. And actually, the gauge invariant, what the gauge invariant guarantee is that the W3 and the A and the B couple diagonally. But after we rotate them, we don't know what happened because it become massive. So actually, I can write, and I really hope that all of you should actually do it. You can write a very nice model where the Z couple in a non-diagonal way. It's very easy to do, actually. So it's really guaranteed. No, it's not. It's nothing to do. The custodial symmetry has to do with the Higgs sector, and actually it's nothing to do with the fact that the Z couple diagonally. So what is really happened that makes sure that the Higgs couple diagonally? So the G mechanism is actually very important. And the G mechanism, if you like, is very directly part of the unitarity of the CKM, and it's actually very much related to the question why the Z is not coupled diagonally. And actually, what happened, and it's a really cool thing, is then if the Z were not coupled diagonally, then we have violation of the G mechanism. I will talk about the G in 10 minutes. But in model building, can you think about what's really in the standard model and make it really clear? Yes. Yes, very, very good. Yes, yes. Let me explain it one more, the way I explain it, but it's basically what you say. You're absolutely correct. So at the end of the day, what guaranteed that the Z coupled diagonally is the following very interesting situation. So we all know that in the standard model, we know that electric charge Q is equal to T3 plus Y. And what things can mix? when we do a rotation, a basis rotation, clearly we can only rotate things that have the same quantum number under the unbroken symmetry. I cannot mix a charge 1 and a charge 0 fermion. I can only mix all the charge 1 or all the charge third, right? And I cannot mix a color triplet with a color singlet. I can only mix states that have the same quantum number under the unbroken symmetry, right? So in particular, when I talk about the fermions, I can only mix things that have the same electric charge. Clearly? Yes? However, in principle, they don't have to have the same T3 and Y. All they have to do is that they have the same sum. The T3 plus Y of all the things that can mix have to be the same. In principle, I could mix things that have different T3 and different Y, but they can still mix as long as the Q is the same. However, what's happened in the standard model? In the standard model, all the quarks that have, say, charge 2/3, not only that they have the same charge, they also have the same T3 and the same Y, right? Because the 3 generations are identical, I can actually, I get this interesting situation that all the charges, all the fermions with the same charge happen to have also the same T3 and the same Y. And because of this property, the Z coupling is diagonal, okay? And I'm not going to prove it to you. I have a little really cute homework, and I really hope you can do it. Just add what we call vector light quarks to the standard model and just see that it work differently. Let's say that I have what we call a non-sequential fourth generation, okay? Instead of having a regular fourth generation, I have another one that I call it T prime L, which is a 3-1 and a third, and and a 2/3, and T prime right, which is 3-1 and 2/3. Okay, so this is a vector-like generation. I can write a mass term for this, for the two of them. Okay, and in particular, this guy TR couple like the rest of the U of the up-type quarks. And what's happened? This one still have an electric charge of 2/3. Let's look at this one. What is the electric charge of this TL? The electric charge of this TL is 2/3, right? But the T3 of it is 0 and the Y is 2/3. So I have a charge Q/3. The rest of the up-type left-handed quarks, T3 is half and Y is 1/6. That give me the 2/3. So this one, this TL prime, have the same Q, but a different T3 and a different Y than the rest of the left-handed up-type quarks. Okay? You just add it to the standard model, add these two terms to the standard model, write the most general mass matrix, okay? Diagonalize it, work out the coupling of the Z, and what you find out is that the Z coupling is not diagonal, okay? And if you like, I have it right, with nice item with answers and everything, because I gave it, I think, to all the students in all my classes. It's a really cool one, it shouldn't take you more than half an hour, okay? But that's the important point. The important point is that we have this thing, okay? Yes?
Before electric symmetry breaking, you have U1Y, right?
Yes,
And part of it goes to Z and part of it goes to gamma.
that's right.
And doesn't that imply that they both should have the same kind of coupling?
So the coupling of the Y have the same coupling, and what we're saying is completely correct. Before electroweak symmetry, TL prime cannot mix with T prime, with T, right? Because before electroweak symmetry breaking, that's what we have, right? So these two fields cannot mix before electroweak symmetry breaking. After electroweak symmetry breaking, because the Higgs acquires a wave, the up component of Q left can mix with the T prime L, right? So what you are saying is completely correct, that before electroweak, the U1Y, the B field couple only to this and only to this, and there's no mixing. The B field cannot really mix them. But the physical Z can mix them.
Sure.
Okay?
And I was wondering if that implies that you cannot couple it with a C because the gamma has they both combine.
Oh, okay. So at the end of the day, what we call a U and a C is a standard model U and C, right? Now, if you add these kind of fields to the standard model, then what you would call a U should have in general some T prime component. So the U that you have, it's not our U, right? And this U and that C, because then you have a U and a C that both of them have some T prime component, then they can have flavor change in neutral current. Okay? So, yeah, if you have some time, really, try to do this. Just add those two fields to the sample and do what you did in the past and just follow the, the standard diagonalization procedure and see where you end up. Okay? So when we talk about the Z coupling, the word that we use to describe why the Z have no flavor change in neutral current, we use the word of universality. Okay? We say the reason that it doesn't have flavor change in neutral current is because the coupling of the thing under it are universal. Okay? So let me write this word. That's universality. Universality. And it's important because when we go to do beyond the standard model, again, we're exactly going to use this property of universality, just like the standard model is using here. Okay? Good. So you kind of see, if you like, the way to go is just, the standard model, just write it down and keep doing but then we see that the reason, there's some of deep reason. The standard model have no flavor change in neutral current because it's only one Higgs coupling and because the three generations are what we call sequential three generations. They are exactly the same. And if we put what we call a non-sequential fourth generation, if we put some other quarks that have different quantum number, we will have flavor change in neutral current. Good. So we understand why there's no flavor change in neutral current in the standard model at tree level. But of course, we should have that at one loop. Yes? Of course? Everybody agree? Yes? Okay. Why of course? Because we know that flavor is broken by charge current interaction at tree level, and therefore at some loop we must have it also at anything, it will be generated. And the question is what's happening at flavor changing neutral current at one loop. So I want to discuss FC&C at one loop. And what we're going to find out is as following. Naively, when you say things are one loop, what immediately jump at you? What is the suppression factor? When I tell you, oh, something is one loop, you should say, therefore it's suppressed by? That's everybody know, huh? That I don't have any problem of, like giving you hints, waiting. Right? 1/16 pi squared, immediately it's one loop diagram, right? So you would say, okay, FC&C, that's for it's 1/16 pi squared, also known as 1/100, okay? So it's about 10 to the minus 2, right? So you would just look at flavor changing current and says they should be suppressed by about 10 to the minus 2, and that's it. And you just go to the data and you find that the data, the flavor changing neutral current in some cases are suppressed by much, much more than this factor of 1/16 pi squared. Okay? And what I want to explain now is why actually in the standard model this suppression is much bigger. And 1/16 pi squared, this suppression is suppression in any standard model. It's not related to the parameter of our standard model. And the other factors are related to our standard model, to those small parameters. Okay? And let's go under the famous G mechanism that I'm sure all of you heard about it. Maybe even if you don't fully remember, you for sure heard about the G mechanism. So let me try to explain the G mechanism again, kind of where it's coming from. So the prime example of the G mechanism is, let's look at the process of KK bar mixing. So we look at the amplitude that takes a kaon into an anti-kaon. And this is a flavor change in neutral current because it's the same charge. And we start with, say, a kaon, S d bar, S bar. That's a kaon. I don't know why, but this is the convention. The kaon have the S bar. The heavier quark is the bar when we have the kaon. And then eventually we want to make it into a K bar. Okay? And let me plot what is called the box diagram. Why it's called a box diagram? It looks like a box? With arms, yeah. Like the penguin look like penguin with arms and whatever. Physics is abstract. Our art is abstract, right? Never try to explain why it's penguin. It looks like a penguin. It's abstract. Okay, so that's the box diagram. The bar should be here. Good. I just want to make sure you are not sleeping. And so, this diagram, actually, there's two of them. You can also replace, the quartz core like this. But that's the leading order diagram that gives me K to K bar. And you just go in and you calculate this diagram. And what you do, you just said, okay, what's really going here? This wavy line are two W's. Okay? And what go on here in the upper one, they are like uptype quarks. Which uptype quarks? Of course, the very first thing you learn in quantum mechanics is you write all the amplitude. You first add them and then square. You remember? Very good. I know. So you have to put all the uptype quarks here, right? So let's put here U, C, and T. And let's put here U, C, and T. Okay? And you add all those diagrams, and that give you the amplitude. It's important that what we care about is the amplitude. It's not the branching ratio. You don't take the amplitude and square it. Okay? I will hopefully will have time in my last lecture to actually get into more details into this. So we do this, and what we find out that we have here 4 CKM elements, right? In each of these vertex, we have a CKM element. And when you write it down, you find that the amplitude, therefore, is proportional to the sum over VIS VI D star. That's come from the uptype, the sum of I, from the upper one, and then from the lower one we call VJS VJ D star. So we have also sum of J, because we have one here and one here, times some function that must be proportional to the masses of what's running in the loop, Mi and Aj. Okay, so all this is under the sum. Yes? So of course, one really nice thing to do is actually to calculate it. And the way to calculate it is you use Feynman diagram rule, why you write the propagator k slash plus m, and you do it, and it's really cool, and you calculate what f is. But I don't want to do this. I want to try to argue that we can get some properties of f without actually calculating. We cannot really get it all, but we can get some properties of f without ever calculating it. Okay? So the first thing that we have to note, we have to use the fact that the CKM is unitary. And since the CKM is unitary, what we can say about the case where f would be a constant, if f was independent on the masses. So I'm asking if f is a constant, if f of mi mj equals just a constant, what I get for a? A is equal to 0. Why, if f is a constant, a is 0? Because if f is a constant, I can put the f outside the sum, and then this sum is 0 times 0, actually. It's 0 squared. Not that we care much. Once you have 1, 0, you go home, right? You don't. But do you see why it's 0? It's 0 because of the unitarity of the CKM. The unitarity of the CKM tells me that the product of two rows, a row times the row complex conjugate, is 0. That's a property of unitary matrices, right? So if we take this f out of then we get it to be 0. Yes? So what we know about f, again, without doing any calculation, just what we know about calculating Feynman diagrams. So we know that if it's a constant, that means that in the limit that all the masses are the same, then it's 0, right? So therefore, it must be somehow sensitive to the difference between the two masses, right? And it should be sensitive to the difference in the two masses, such that when the difference goes to 0, the amplitude goes to 0. So the difference between the two masses cannot be in the denominator, right? It can only be in the numerator. Yes? So just based on this argument, I know that if I take these masses to be small, okay, that's, let me say. Now I make an extra assumption. Said what is in the denominator? I know that we have the mass of the W, right? So let's forget about the top for the minute. And I should have started like this. I want to forget about the top just because I know that numerically the CKM coupling to the top is very, very small. So let's assume that I forget about the top. And all I have is U and C. So I only consider U and C quarks. And the mass of the U and the mass of the C are much, much smaller than the mass of the W. So then I said, okay, I know that I can expand in those small parameters, okay? And just based on the fact that I know that when the mass of the U and the C are equal, I must get 0, I know that it must be some function that is polynomial in the mass of the charm. Yes, because I make the expansion. So far, I didn't do any calculation. It's just based on this. So based on this, I know that f, say f of m I m j, have to go like the mass of the quarks to some power. Okay? And this power could be 1, 2, 3, and 4, etc. And it's turned out that this number is 2. Okay? So when you do the calculation, you find out that to leading order f goes like mc squared minus mu squared over mw squared in the dimensionless sense. Okay? So I hope that you see how I got this. So I was unable to explain why it's mc squared, but I was able to explain to you why in the limit at mc equal to mu, this function must vanish. Okay? It must vanish because of this unitarity of the ckm. Okay? And it's turned out that it's mc squared. This goes under the name of the G mechanism. Why it goes under the name of the G mechanism? Because there are 3 people who are the initial. But what they did is the following. In 1970, the charm was not discovered yet, and only U, D, and S were known. And then people didn't understand why diagram like KK bar mixing is so small. And they said, if we have a charm, then we get this much higher suppression that go like mc squared over mw squared. Okay? So they assume the charm exists, and therefore they get this kind of things. Now, in retrospect, the way we call the G mechanism said, G mechanism is direct consequences of CKM unitarity. Because the CKM is unitary, this function must be proportional to the mass of the internal quark to some power, and therefore we have this extra MC over NW suppression. Okay? Yes? Any questions? No? You should ask, because then I'll ask you a question if you don't ask. No? Yes? Because when they are diagonal, actually, yes. Actually, I have it here. Okay? I have my usual joke is that I said, anyway, I can show you, but you won't understand because it's in Hebrew, but I cannot run it on you. Okay, so let me say it. Lama chayavim pitzul b'masot, which translates, why do we need non-degenerate masses? So I have it here, okay, and I'll show you. Okay, so that's actually the question, and here it's with the question mark, mean I should ask it the students, okay? So why should we have non-degenerate masses? What happens if the masses were degenerate? Okay? Then that's the case of the F is a constant. Right, because we don't really care about the masses. As long as the masses are the same, then we can take this and put it out of the sum, and we get 0. Right? So what we care about is the non-degenerate of the masses. Okay? Because then we can actually take this F and put it outside the sum. Because the masses are different, then the sum, each term on the sum is different. When the masses are the same, we can take it out, and we get the 0 from the CKM unitarity. That's right. So what I'm saying is that so this one, you can write as MC plus MU times MC minus MU, right? So what I'm saying is that I don't know the exact form of F from this argument. All I know from this exact form of F is that you must have some form of some power of non-degeneracy. Okay? So it's happened to be this, and that I cannot explain based on hand wave argument. For this, eventually you have to do calculation. Sorry? Yeah, you could have log, okay? And actually, in this case, you don't have a log. But if you look for things like B2S gamma, you get logs, okay? So you could have logs instead of powers. It's completely right. And it's go under the name of hard gym and soft gym, etc., etc. There's much more to the story, okay? All I want to say is that if the masses are the same, when you have the general masses, we don't have it. So it must be proportional to somehow, and it's end up to be MC squared in this case. For this, we don't have hand wave arguments. You have to do the calculation. Okay? Good. So let me ask you one more question. So what we find here, so we can forget about the mass of the U. Let's forget about the mass of the U. We find that the KK bar mixing, this amplitude, end up to be proportional to 1 over 16 pi squared time mc squared over mw squared, that's additional suppression, time all the ckm that we have, right? So we have other ckm, which end up to be something like VUS, VUD, absolute value squared. This is 1, but this is sinus theta Kabibo. So we see that we have this really extra suppression. This one is suppression that we get from one loop in any standard model, and these two are specific to this standard model that we have in. Yes?
Shouldn't it be VCS? Like, isn't the C contribution the dominant one?
Oh, so actually it's both, they are the same. So in two generation, VCS, VCD is the same as VUS, VUD.
Yeah, I agree.
Right? But you're right. We should do it. Actually, what really enter here should be something that's completely basis independent. We can actually write it. We can discuss it much more, like anything. Okay? But the point is that at the end of the day, we see this extra suppression. Good? What I learned it. As advertised. Haha, we get this extra suppression. Right? Everybody happy with this? Good. I also kind of happy. It's good. It's good to be happy. But I want to ask you a question, okay? Have you heard about the decoupling theorem? Everybody heard about the decoupling theorem? The decoupling theorem states the following obvious statement. It said if you have some physics that it's at extremely short distance, you shouldn't care about it, right? We shouldn't care about what's happening at the Planck scale when we do, particle physics. And in particular, when you do condensed matter physics, you shouldn't care about what your friends at high energy physics are doing. Sometimes they indeed don't care, which is a problem, right? But I mean, because this we call scale separation. It's very, very important in physics. When we do something, we don't care about higher order. That is, if you have some new particle, the effect of the new particle must come in the denominator. And here we have KK bar mixing, and we find this really cool result that when I take the mass of the charm higher, I get a larger effect. And that's very counterintuitive. Just think about this loop diagram. When I have things that run in the loop that are heavier, we expect the result to be more suppressed. It violates the decoupling theorem. Yes? Oh, so what's happened, let's say, if we have if I take the mass of the, what you are saying is the right answer. It's related to this, okay? So let me say it my word. What you are saying is correctly the right answer, okay? I want to say it my word. So what he's saying, we have the mass of the W. You cannot play this trick on me. And said, let's take this one up and just, you have this one. You cannot think as this one is not there. Okay? Actually, I could not write it because it's in the prop. That's this prop. I could put it in the prop, right? Because it's proportional too, so I could put the NW in the proportional too, and then you would notice, but you would know it anyway because it must be 1 over NW squared. So the answer is that this doesn't violate the decoupling theorem because what's really happened is that this whole story has to do because of electroweak symmetry breaking. Okay, and what's really at the end of the day, you can think about what's happened is that it is the Yukawa coupling that plays a role here. And when you take the mass of the charm to be heavier, what you really do is you take the Yukawa coupling of the charm to be heavier. And that's not a violation of the decoupling theorem. The decoupling theorem tells you if you just take a mass of a particle to be heavier. But of course, if at the same time you also take the coupling to be bigger, you don't decouple. The decoupling is if you just take the mass and doesn't change anything else. Here, this is not the case. Changing the mass of the quarks always also change the Yukawa coupling. And the Yukawa coupling is a coupling, and therefore you don't have decoupling. Okay? So that's an important thing about playing with decoupling when we have spontaneous symmetry breaking. You have to remember this.
C alone got extra contribution from heavier Higgs.
Oh yeah. So you can play those games and you say let's assume go beyond the standard model and they have extra Higgses, extra stuff, and then you will have more diagrams, right? What I'm
I've seen this proof in decoupling theorem when Higgs is involved. When you increase the coupling to the top, for example, it doesn't decouple because you increase the coupling also. But you don't see the Yukawa coupling for the charm with the Higgs explicitly in it?
Exactly. So what would happen? So that's a very good question. Let's say that the charm gets its mass not only through the Higgs mechanism, but there's also bare mass term for the charm. I had a C left that is a singlet under SU2, and therefore I can write a C left, C right term, and I could write it here. What would happen if I have a mass of the charm that comes not from the Higgs mechanism? How we solve this paradox? Is that the question? Yes. So I have a model. In this model, instead of having the charm get the mass the usual way, the charm get the mass by having a bare mass term. Let's go like Cl, C right. Both of them are singlet of SU2 left. The CKM is look different. The CKM is not even unitary. You have flavor changing neutral currents through Z exchange. Okay. So it's a whole different story. Okay. And actually, it's the really nice what's happened is the 3-level versus the 1 loop and how they interplay with each other. So it's just this story that I was telling you is just not valid in this case. And actually you look at it and you find that the mass of the charm completely decoupled. So you can take the mass of the charm to infinity, and what's happened here is not the mass of the charm. What will happen here is something like the mass of the charm times some mixing angle, and when you take the mass of the charm to infinity, the mixing angle also goes to 0. Okay? So at the end it's all working. Yes. So you could think about it. So of course it depends on what gauge you decide to do this. So if you do it in some unphysical gauge, you actually see that you get these things coming from the coupling of the ghosts. Okay? I love physical gauges most of the time. And the way I like to say it is just this, that in the theory as a whole, when you take the mass of the charm to infinity, you also at the same time increase Yukawa coupling, and therefore the coupling should not work. But it's completely correct. Another way to look at it, and for some people it might be much nicer to see it, is to look for some unphysical gauge where you have the ghost and you see that the ghost coupling like the Yukawa, and it's the longitudinal component of the W that actually give you the effect. And you think about them as the Higgs. Okay? Any more question on this? Yes. About? What about the top quark? That's so good. Because I told you I make the assumption that I don't care about the top quarks. And always when you make an assumption in the beginning of the calculation, what you have to do at the end of the calculation, to check if your assumption is actually correct or not, right? So you look into this calculation and you plug it in and you find that the effect of the top is about 1% or 5% compared to that of the charm. Okay? And the reason is that the Yukawa that the mass of the top, you say, the mass of the top is about 100 more than the charm. So you have mt squared is about 10 to the 4 larger than mc squared. But in terms of the CKM, it's much smaller. Shall we do it? No, we should not do it. Let's do it. Yeah. That's I thought you were asking something else. Yeah, you cannot make this assumption anymore. And then you have a function like, these really nice functions that go like 1 minus 8x squared plus 6x to the 4 log. You love those functions, right? Yeah, so you have those functions So actually you do the calculation and what you find that this function, and it's about, if you just make this approximation, the fact that m top is twice mw, and if you instead of writing mt squared over mw squared, you write the full function, it's an error of order 3. Okay? Not so big. But of course, you know how to calculate those functions. Okay? Actually, it's called Inami-Lim functions because Inami and Lim were the first people who actually calculate, because until sometimes in the 70s, or I don't remember when the paper came out, everybody made this assumption that they are much smaller than MW, and nobody ever believed that the top can be heavier than MW, so nobody cares about. And then they make this bold assumption that the top can be heavier than the W, and write a paper with just calculating all those functions, and everybody know them as the Inami-Lim function, and you go and you find those functions somewhere. It's basically some loop integrals with some, Okay, so that's basically all I want to say about flavor changing neutral current. And the bottom line about flavor changing neutral current is as following, okay? It's probably the big deal about flavor is the fact that we don't see flavor changing neutral current. And the reason is the following. The standard model is built such that there's no flavor changing neutral current at 3 level. And on top of it, at one loop, we have this really the gene mechanism that give us this extra suppression factor. It's a small CKM, and in some cases, some small mass ratios. Okay, so flavor chain neutral alkynes are highly suppressed in the standard model, and that's what we see in nature, and that's why it's such a big deal when we go and move and discuss things beyond the standard model. Okay. Everybody appreciate flavor change in neutral current? Yes? Good. That's good. Yeah. So if the two quarks are degenerate, then then this amplitude is completely vanishes, right? So if mu is 0 by itself, it doesn't make any difference. What is important is if mc and mu are degenerate. In particular, if both are 0, then we don't have flavor change in neutral current. In order to have flavor change in neutral current at one loop, we need that the masses are non-degenerate. Actually, let's explore this point a little more. Do you see from a symmetry point of view why if let's say all quarks were degenerate, we will not have flavor change neutral current? We will recover the U1 cube, right? Yes? So if you like, flavor change neutral current must be proportional to the breaking of the U1 cube that I was kind of starting the lecture with. Is it clear? Right? Because if it's just what's happening in the lepton sector. When the neutrino are degenerate, and we don't really care about the fact that the neutrino are massless. What we care about is that the neutrino are degenerate. Because the neutrino are degenerate, we gain the U1 cube. And because we have the U1 cube, there's no flavor change in neutral current at all. Right? Because each flavor is completely conserved. Right? So if the masses were degenerate, then the CKM would be diagonal, and there will be no FCNC at one loop and two loop, etc. Yes? Oh, U3? No. U1 cube just means that each of the flavor is by himself. U cube say that all of them can mix together. Okay? More question on FCNC? There's a lot to do, but we'll move on. So, the next thing I want to talk about CP violation and how CP violation is so important when we, yes? So again, if the quarks were degenerate, let's assume that only one type of them are degenerate, right? Say the up type or the down type. And then it's just like neutrino oscillation, right? And if the neutrino were degenerate, there will be no neutrino oscillation, right? So in order to have neutrino oscillation, you must have that the neutrino are not degenerate, okay? So FCNC and oscillation are very, very much tied together. It's just a matter of time scale. If the oscillation is very, very fast, we call it FCNC. If the oscillation are small, we call it oscillation. Okay, so let me move to the question of CP violation. And as we talked about, naively, the story of CP, T, CP, all this has nothing to do with flavor, right? There are symmetries that, when do we learn about them first? When we first discuss CP and T, right? I think it's section 3.6 in Peskin, right? Before he didn't even mention flavor, right? Flavor is somewhere in, don't remember. It has to do with the understanding of the Lorentz group and how the Lorentz group actually acts on fermions and these kind of things. And it apparently has nothing to do with flavor. And indeed, we don't expect anything with CP and CP to do anything with flavor. And if you ask questions like what's happened with P or C violation, this is, in a way, has nothing to do with flavor. Right? So you actually can study about P violation, and you study P violation in, for example, in leptons. You can actually, although historically we find P violation in in some beta decay, we could find P violation in muon decay, right? You can do, and there you don't have flavor at all. Flavor is diagonal, everything. P violation has nothing to do with flavor. It's just the fact that left and right-handed fields have different quantum number under SU2 cross U1. It's completely the gauge structure, right? It's nothing to do with the fact that we have several flavors. Yes? However, CP, it just happened, while it doesn't have to be the case, in nature, CP only happened in processes that also violate flavor. Let's say it doesn't have to happen, but that's what happened for us. Okay? So now we ask the question, how CP violation? That's why when we talk about CP violation, it's always come in flavor lectures. Okay? Although in principle, in a different world, it would not have. Right? There was one lecture on CP violation and another on flavor. But in our world, it's come together because it's CP violation appears only in something that violates P. Sorry? Oh, philosophically, it's weird. Actually, we can talk a little more about philosophy. I will talk a little bit more about philosophy. But the next hike, yeah. Next hike, we should talk about philosophy. So my son took a philosophy class, and then he said there was a big philosophical question. He came back home and he said, wow, I'm so lucky that I'm a hiker. My son is much, much more a hiker than I am. And he said, they discussed for several lectures the question of the river, the philosophy of the river. Can you say that the river is the same? So if the water, can you say is the same river? Because the water in the river are different now than the water before. You know this philosophical question? No?
Never shower in the river, in the same river twice.
Yes, yeah. You never, because it's a different word. And so I told my son that I'm not so sure because it's a deep thing in physics that all electrons are the same, right? Fundamentally. But, anyway, we had a long discussion about this. What this has to do with CP violation? Nothing. No, it was, it was your question. That was my philosophical remark. Okay, so now we say that one thing I want to say, we discussed CP violation, but just as a remark, I want to mention that C and P are violated in any standard model, because in any standard model, the coupling of the left-handed and right-handed field couple differently to the double and under SU2. So C and P are violated in any standard model. CP, however, is violated only in our standard model and in many other standard models, but it doesn't have to be violated in any standard model. So that's what we're going to discuss. What are the conditions that we have CP violation in any standard model? And the answer is, anybody know what is the answer? What is the condition to have CP violation? I'm gonna be more precise and I'm gonna give you all the conditions, but probably there's one condition that maybe not all of you, but many of you knows. At least 3 generations. That's in the standard model, that's true. But I want something a little more. What CP violation always come with a phase, right? CP violation always come with the fact that we have a phase. So CP violation just means that you must have a phase. And I want to give a very hand-waving argument of why we need a phase. Okay? And the hand-waving argument is the following. So let's say that I have some Lagrangian, and I write my Lagrangian in the following way. I have some Lagrangian like this. And then I'm going to do something that you never seen before. Okay? What you always see when you write this Lagrangian, in the beginning when you are really, really young, sometimes, not always, sometimes people write this. You remember this? We don't write it anymore, right? But now I'm going to do something that probably you never seen before. I want to write it. you know how to write it? You write plus the Hermitian conjugate. So you write the Hermitian conjugate explicitly. B left bar, AR. That's the Hermitian conjugate. And now you ask the question, what CP is doing for a fermion bilinear. So what you do, you open Feskin chapter 3.6 and you see what it does. And what it does is actually CP take AL bar B right into B left bar AL. Okay? So this Lagrangian under CP. I was so close. I had an error-free game until now. I learned also baseball in my years in the US. My first baseball shirt that I bought to my kid was the Colorado Rockies shirt in 1994 when I was here. I didn't know what it is even, but then I know everything. Okay. Now we are in 7 inning. No, bottom of the 7. I was error free, and then boom, right field instead of left field. Okay. So under CP, what's happened? This one become y b left bar a right plus y star a left bar b right. And you see the following obvious thing, that if this Lagrangian and this Lagrangian are the same, if y is equal to y star. Okay? So if y is real, then the CP, when we apply CP on this Lagrangian is stay invariant. That means the CP is a good symmetry. Okay? Why I said that this is a hand wave argument? The reason that this is a hand wave argument is that there's always the possibility to do a phase redefinition. Okay? So what is the true definition of a Lagrangian that conserves CP is that there does not exist any basis where this y can be, that all the parameters are real. Okay? You can always make some parameters real. But as long as you don't find any basis that one of them, that all the parameters are real, then CP is violated. Okay. So we understand that CP has to do with phases, and now we're going to play a little bit with phases and these kind of things. Okay? So let's move about and talk about CP violation in the standard model and why CP is violated in the standard model. What is the condition that CP is violated in the standard model? And we already heard, and I guess all of us know, that in order for CP to be violated in the standard model, we need 3 generation. And the reason is that if you think about how you parameterize the full standard model, and in particular all the flavor parameters, we mentioned it last time, and I don't really go through the formal proof, but in my notes that I have a write-up about this. And you find that in order the parameters, you must have one complex parameter. And in particular, the way we usually write this one complex parameter is the one phase of the CKM, right? The CKM is parameterized. We choose a basis where all the masses are real. Of course, we can choose another basis. But we choose a basis that all the masses are real. And the CKM, which is a unitary matrix, is parameterized by 3 mixing angles that are real and one phase that is called the Kobayashi-Maskawa phase. And it's this one phase that gives CP violation in the standard model. Okay? Good. So now we want to ask the question of, remember last time we said that CP violation is somewhat small in nature, and I want to discuss how this smallness appears in the standard model. Okay? So what we really after is the following. What I try to do now, I want to give you some basis-independent measure of CP violation in the standard model and argue that it is small in some way. Okay? So in order to have CP violation in the standard model, what we must have, okay? We must have 3 generation. So we must have, first we must have a phase. Second, we must have 3 generation. Why we must have 3 generation? Because it's in 2 generation, you can just rotate the phase away. Okay? And actually, the third thing that we must have is that all the quarks are non-degenerate. Okay? All the quarks from the same charge are not degenerate. I mean, we could have that the S and the C are degenerate. That's not a problem. But the D, S, and B are not degenerate, and the U, C, and T are non-degenerate. So we must have non-degeneracy. Why we must have a non-degeneracy? Because if we had some degeneracy, again, we could rotate away one of the parameters of the standard model. We have an extra symmetry, and since we have an extra symmetry, we have some less parameters. So these are the things. We must have a phase, a 3 generation, and all of them are non-degenerate. Okay? So what we conclude out of these things, okay? What we conclude out of all of this is that the CP violation in the standard model must be proportional to all the CKM elements, right? Because if some of the mixing angle were 0, then effectively we'll have a 2-generation model. And it must be proportional to all the mass differences of all the masses. Because if some of them were 0, then we will not have CP violation. Okay? And then we see why CP violation in the standard model is small. CP violation in the standard model is small, not because the phase is small. The phase is actually order 1. It's more because in order to involve all the 3 generations, we must involve very small CKM elements. And in order to take account on the fact that the masses are non-degenerate, we must involve also all the delta m's. And some of the delta m's are very, very small. Like ms squared minus md squared is a very, very small compared to the weak scale. Okay? So we see how in the standard model these are kind of small numbers. And I want to talk a little bit about how we actually parameterize it. And I want to introduce few things. The first things I want to introduce, it's what we call the Jarlskog invariant. Maybe you heard about the Jarlskog invariant. She's from Sweden, so we start with J, but you pronounce it with Ya, as far as I know. Anybody here from Sweden? No? Nobody have connection to the Nobel Committee? You can speak some Swedish? It sounds good. I can say it correctly, Jarlskog. Yeah, the Jarlskog invariant. And Jarlskog, and what she showed is actually that in a basis independent, no matter what, there's some measure of CP violation in the standard model, and this measure of it's invariant under any basis rotation, and the value, it's called J for Jarlskog, and in the standard basis, this Jarlskog invariant is equal to this, C12, C23, C13 squared, S12, S13, S23, sinus of delta Km. Okay? So this is some measure of the CP violation. And now it just seems like, I just make, and with this C of theta 1 result is the angle of the unitarity triangle. So far it doesn't look very, very impressive. The point is that this one is invariant under whatever parameterization of the CKM that you want to do. And actually, what it turns out, and that's kind of a cool result, is that it has a very nice, it's a very nice geometrical interpretation. Okay? And the very nice geometrical interpretation come under the name of the unitarity triangle. Maybe I should stop and say one thing before. One thing before is that you see that this is small, right? And it's small not because delta Km is small. It's small because we have all this sign of the angles, and because the angles are small, that's why we are small. And that's actually taking into account the fact that we actually need the 3 generations, and we need all these mixing angles, okay? So that's where this Jarlskog invariant play a game. But it's actually related to something else that we call the unitarity triangle. And what are the unitarity triangles? And unitarity triangle, it's a very cool concept to just make this statement kind of nicer. Since we know that the CKM is unitary, we know that we have unitarity relation that we already use up there. And how many unitarity relations we have when we have a 3 by 3 matrix that is equal to 0? So I have 6 of them. 3 rows, 3 combination of rows and 3 combination of columns. So in particular, I can have something like this. VIX, VIY star equal to 0, or the other way around. VXI, VYI star equal to 0. Sum over I. Okay? And since this V, we have 3 complex vectors, you can represent them as a triangle in the complex plane, right? And this triangle in the complex plane is called a unitarity triangle. Why a unitarity triangle? Because a triangle, they come from a unitarity relation. Okay? So I have 6 of those unitarity triangles, and I plot them like this. Why I plot them like this? Because that's how I plot a triangle. Okay? Now, what is become really nice is the fact that actually, in the standard model, you can show that all 6 unitarity triangles has the same area, and this area is equal to J over 2. Okay? So the area of all unitarity triangles are equal to this measure of J. So this is invariant, and all these unitarity triangles are the same. And then you actually take this unitarity triangle and you plot them. So let's take two unitarity triangles and plot them. Let's take the first unitarity triangle is the SD unitarity triangle. So in the SD unitarity triangle, what we have here VUS, VUD star plus VCS, VCD star plus VTS, VTD star equal to 0. How this triangle gonna look like? Okay, remember how the CKM looks like when we have connection between the first and the third generation. It's very, very small. Okay, so in this unitarity triangle, this one is of order is kind of large. This one is large, but this one is extremely small. Okay, because this one connect second and third generation and first and third generation. So this triangle looks like this. It looks like a triangle. Well, kind of. Let's ignore this kind of thing. And then I want to do another triangle. I want to do the BD unitarity triangle. And in the BD unitarity triangle, what you find out that all the three sides of them are roughly the same order. And this other unitarity triangle look like this. Okay? And can you tell that the area is the same? Yes? Can you tell? You cannot tell? You die. I counted on you and you say you cannot tell? Okay, let me explain. So here the height is small, but the base is large. And here both the height and they are small, and they are the same. Okay? The point to make is as following, okay? All of those unitarity triangles have the same area, but some of them are very, very squished like this, and some of them look more like a regular triangle that you see every day, right? And when we talk about unitarity triangle, this unitarity triangle have a special name. It's called D-unitarity triangle. Why? Because it looks like a triangle and the rest, these unlikely triangles. Why do we care much more about this one? Because when we try to measure phases, it's much easier to measure phases of this kind of a triangle than this kind of a triangle. Is it? Right? Because you have experimental error. When you have experimental error, it's very, very hard to measure, to construct such triangles. But such triangle, it's kind of easier. But of course, in order to generate this kind of triangle, you have to measure three small numbers. Here, you have to measure two very, very large numbers and one very tiny number to a very, very high accuracy. Okay, so we learn about the unitarity triangle. I guess I need 2 more minutes to finish the standard model. Can I go 2 more minutes? Yes? I just have this one last thing I want to say. Sorry? Oh, it depends which one of them and depends how you do this. But the bounds are of order 1%. Okay? So, and depend on which, so it's clearly different if you look on this. But we know quite well that they look close to a triangle. Yes? No, absolutely no. And I really confuse, and that has to do very much with the way we choose what we call the standard parameterization. And if you like, is when we learned the Euler angles, you remember? And one angle was different than the other two, right? It's somehow related to this. It's not exactly the same. When you think about an Euler, you have 3 rotations. They are not all of them the same. And I don't have a better, but I definitely spend time thinking. And why it's only in the cosine and not in the sine, I don't know. But then I just said, there's just one parameterization. Who cares? That's what I care about. All the areas are the same. The space is independent. Probably I should not even mention it, right? I should just say there's something called J, and it's related to this area of this unitarity triangle. And then it's nice, right? So let me just mention the last thing is the following. So we know that the CP violation has to be also proportional to the masses. So at the end of the day, CP violation must be proportional to the following thing, okay? And there's one little thing that I don't know about why it's the squared, but it must be proportional to the following thing, to the product of all the delta m squared ij in the up sector squared time delta m squared ij in the down sector time j. Okay? So what I'm saying is that it must be proportional to all those factors because j gives me the size of the ckn that has to do with the fact that I need a phase and I need 3 generation. And this product of delta m's take care of the fact that if 2 of the masses were degenerate, then I would get 0. So therefore, it must be proportional to the difference, and the same argument that I gave you up here, that is end up to be squared, and I don't know why. You have to do the calculation. You get that it's squared. Okay, but it doesn't matter really. All I'm caring is that it must be proportional to some delta m's. Okay, and that's really, really why this is very, very small number in whatever units.
So
Yes.
If two methods are degenerate, but you get one of the signs to be 0, so that but you get the z already 0.
I thought that sign, because S is our sign of the mixing angles, I think you have degenerate.
So I'm confused now. So I know. I exactly understand the question. I say I'm confused, and it's already I'm going over time. So I will try to. I have to think about it. I don't have an answer. The last thing I want to say is the following. So this is what we know. This is kind of the small overall thing. But at the end of the day, we can still get a large CP violation, right? We can measure CP violation, sinus 2 beta, some asymmetries of order 1. So this is the CP violation that we have in the standard model. And it's small, but some of this smallness we can take care of if we actually use small branching ratios. So if, say, we use some small branching ratios, it's not the CP violation that we have. The total is small. So what we really care about, that the total number of events that we need in order to establish CP violation somehow have to be proportional to this kind of a product. Okay? But it doesn't have to come only in the CP violation that we measure. It has to come in everything that we put together. Okay? So the explanation is as following. If you ask, when you ask if I have the full standard model, then that's the measure of CP violation. But if I have one specific experiment, let's say I look for k-long decay, then I only care about k-long, then I already projected out a k-on. And by projecting out the k-on, I kind of say, well, I only pay the price because I don't pick up a charm and I don't pick up a bottom. I pick up a k-on, so I already reduced my statistic by picking up only k-ons, so I don't need these factors of the delta m's that stand in front. Okay? Yes.
So what I was asking is that now we have this cinematic source of CP violation.
Yes.
So is there other kind of mechanism to violate CP because it's related to T violation?
There's many, many ways to violate CP, not in the standard model. The way to violate CP is as following. You must have a phase that is, you cannot remove this phase. That in any basis there exists a phase, then it's CP violation. And of course, this Yarskog invariant, you can go to other models and you can find that in other models you have 10 or 20 or 30. Okay, so, pick your favorite SUSY model and you can have 10 Yarskogs or 20 Yarskogs or 5 Yarskogs or 3 Yarskogs. And each of them, and in general, they have nothing to do with flavor.
But is there a reason why those are suppressed?
Yeah, so that's what I want to emphasize, okay? So let me kind of conclude and we can talk about it later because I really ran out of time. So that's my first 2 lectures. I wanted to discuss only the standard model. And tomorrow, and that is tomorrow, I'm not making a mistake now, we're going to go beyond the standard model. And let me just emphasize the big picture that we say about the standard model. In the standard model, flavor is special because it's only the W plus that mediate it, okay? It's only there that we have CP violation. And there exist many, many small parameters. And it's this combination of the fact that we have only CP violation there, only charge current can violate flavor, and we end up to have very small numbers. That's why it makes it so interesting. That's why actually it's so hard to go beyond the standard model. So that's what I will start doing tomorrow. I go beyond the standard model. Thanks.